Okay, we are going to jump now into some properties of groups. We are going to start with some very elementary properties of groups. First theorem, uniqueness of the identity, meaning in a group G, there is only one identity element. Okay, and we are going to do the proof. The proof is one of those very elementary proofs too. So let us take one element A, and we do A operation E. I'm going to take only the operation on the left. A operation E equals A, right? That's why E is the identity. Okay, for all A in G. And so first we assume that there are two identities, E and E prime. Okay, I should start here. E and E prime. We assume that there are two identities, E and E prime, and E is different from E prime. Okay, naturally. Okay, so A and A will be an element in G. A times the identity equals A, and A times the identity prime, if prime, the other identity different from the first one, is also an identity, so it will also be equal A. But A equal A, right? So this should equal this. A E should be equal A E prime. Okay, but but this is a group, right? In a group. So since we are in a group, we can, every element will have an inverse. Okay, so inverse times A E equals, I'm going to multiply on the left by the inverse. Okay, this is by axiom 3, right? There is an inverse. Okay, okay, now by axiom 1, since we are in a group, it's associative, so we are going to associate A times A times E equals A1, A inverse times A inverse times A times E prime. Okay, now by axiom 2, right, the one about the existence of identity, or an element times, no, this should be 3, right? This should be 3. The definition of inverse is that A inverse times A equals the identity, right? So this one should equal the identity times identity equals identity times E prime. Okay, but by axiom 2, what is the identity? The identity is an element that if you perform the operation with the identity, the element will stay the same, so this E will stay the same and will be equal to, so E prime will stay the same. Okay, This is by axiom 2, right? I shouldn't write here axiom 2, should be axiom 2 here, okay? Right, so E equals E prime, but that's a contradiction. We reached a contradiction, okay? So we proved the opposite of what we said. What did we say? We said there were two identities and they were different. So that's not true. If there are two identities, they will be the same. And that concludes the proof, okay? So first the proposition was, so the theorem is uniqueness of the identity. In a group G there is only one identity element. So our proposition is, we took two identity elements, E and E prime, okay? So A times E times the identity equals A, and A times the other identity, E prime, equals A. So since those two both equal A, so A times the identity equals A times the identity prime. Then we left operated or multiplied by the inverse, okay, by axiom 3, since we are in a group, okay. But the inverse times A, so now we can associate, right, this by axiom 1. In a group the operation is associative, so we can associate these elements, okay? So we associated these ones, and the definition of the inverse is that the inverse times the element equals the identity, okay? So by axiom 3 this should be the identity and this should be the identity too. Identity. But the axiom 2 says that the identity is an element that operated with another element leaves that other element as it is. So E times E equals E, and E times E prime equals E prime. So we reached a contradiction, right? We reached a contradiction here. Since our proposition was the identities are different, through implications we reached the conclusion that the identities should be equal. So this is a contradiction, okay? So the opposite of what we said is true, and the opposite of the two identities being different is, if there are two identities, they will be the same. And that concludes the proof. Now that this theorem is proved, okay, we can say the identity, okay, not one identity or anything like that, the identity of a group, okay? Usually we write E. The German word, I think, is Einheit. That's the German word for ID, I think. I'm not very sure about this, but I know that E comes from this E here of Einheit. Okay, another elementary property of the groups is the cancellation. In a group G, the right and left cancellation laws hold That is, for instance, if BA equals CA, so we can cancel, right? It's like cancel this. If BA equals CA, that implies that B equals C. If AB if AB equals AC, so we can, it's the left cancellation. That one was the right cancellation, this one was the left cancellation. AB equals AC implies that B equals C. Okay? The proof is also very elementary. Suppose we have BA equals CA. Was that what yes, BA equals CA. Okay, this is a group, so each element will have a inverse. Okay, so BA will have a right inverse. I'm going to put the right inverse on both sides. Okay, so this is axiom 3, right? Each element will have an inverse. Okay, now I'm going to use axiom 1. Okay, BA, so axiom 1 means the operation is associative, right? Here we are. Okay, and now A times the inverse, this equals the identity, right? That's what the identity is. This is axiom 3, right? Existence of identity, and A times identity equals A times the inverse equals the identity. So B times identity equals C times identity. Okay, axiom 2, existence of identities, B equals C. So we suppose that BA equals CA, and through implications we got to B equals C. Okay, that's the right cancellation law, and this proves the theorem. Okay, so since in a group the cancellation law holds, there are several consequences. One is, for instance, if you do the Cayley table, each element will appear one time on each row and column. So each group element occurs exactly once in each row and column. Okay. Another consequence of the cancellation property is the uniqueness of inverses. Okay, and that will be the next theorem. Okay, so this is another theorem, the uniqueness of inverses. For each element A in a group G, there is a unique element B in G such that AB equals BA equals E. So for each element there will be one and only one inverse element. The proof is very elementary too. So for an element A, suppose we have B and C, both inverses of A. Okay, suppose that B and C, two different inverses of A. So A times B equals E, right, since B is the inverse, and A times C equals E, too, since C is another inverse. So E equals E, so AB equals AC, right? A times B equals AC. But now we just proved the cancellation law. So using the cancellation law, B equals C. So we reached a contradiction because our proposition was that B is different from C, and we reached the contradiction. B equals C. So B cannot be different from C. Okay, any element A in G will have one and only one inverse element, and this concludes the proof. So since we proved the uniqueness of inverses, okay, now that we proved the uniqueness of inverses, we can say in a group, we can say the inverse, just as we say the identity, the inverse, since it will be only one. Okay, so it will be the inverse of an element G in a group G. Okay, the inverse of element G in the group G. Okay, and usually what we do is this is the usual notation, okay, like in the real numbers. Okay, this notation is suggested by that used for ordinary real numbers, okay, and the multiplication. Okay, so if we have G times G with n factors, we write G to the power of n. Okay, and we define G to the power of 0 as being the identity. Okay, this is known in basic algebra as any number to the power of 0 equals 1, right? So this is the same idea. Okay, G to the power, this is a definition. Okay, G to the power of 0 is the identity. If n is negative, then we say G to the power of n equals the inverse times minus n. Okay, okay. Now that we saw this notation, the very familiar laws of exponents hold for groups. This means that if we take m and n, and we take a group element G, we have G to the power of m times G to the power of n. We do the usual m plus n, and G to the power of m to the power of n equals G mn. Okay, now in spite of manipulating these group expressions like this one, right, and they are the same, okay, because they coincide with the laws of exponents for real numbers. Okay, but one has to be really careful here, because for groups in general, AB to the power of n is not the same as A to the power of n, B to the power of n. Okay, we're going to see this in another video. Okay, this is very important. Okay, for groups in general, AB to the power of n is not the same as A to the power of n times B to the power of n. Another thing that we have to be very careful in the group operation is with the usual addition. Okay, if we have G, an element in a group, okay, and if the operation is G with addition, the inverse of G will be written this way, minus G. Okay, that will be the inverse element. Okay, so this means inverse. It doesn't mean subtraction. Okay, it means inverse. Okay, likewise, for instance, if you have G to the power of 3, of course this means G plus G plus G 3 times, right? And you can write this as 3G. Okay, and G to the power of minus 3 will mean minus G plus minus G plus minus G. Okay, and this might be written as minus 3G. When this notation is used, we have to be careful with this notation, NG. Okay, because this n here may not even be an element of the group. Okay, this is an element of the group operated n times. Okay, this might not be an element of the group. Okay, because this is not like real numbers. Okay, in an abstract group, a very important thing. This is not like real numbers. Okay, in an abstract group you cannot do operations as G to the power of 1/2. Okay. Now, another thing I want to say is, for instance, for A minus B, in group operation you should write A plus minus B. Okay, because the operation, like here, G under addition, the set G under addition. Okay, so this is not A minus B, this is A plus the inverse of B. Okay, another thing I want to call your attention is for ABC. Okay, in the associative property. Okay, if we have an expression like ABC, you can interpret this as AB times, ABC, or you can interpret this as ABC. Okay, so since in a group all these three they are the same, we can write this as ABC. Okay, because they are equal. There is a proof through induction, and then you repeat this application several times for the associative property, and you prove a general associative property that essentially means parentheses can be inserted or deleted at will without affecting the value of a product. Okay, so I'm going to leave you here a last example, like a squared bc d b squared is equal to a squared b, so b can be here. Okay, now I can associate CD, for instance, and put b squared here, or I can do a squared b, associate these two, leave CD associated, times b squared, or so a squared I can do a b c d b b, right? And now I can associate it, for instance, this way. Okay,